sort of stuff. And that was great. That was really sweet. It finally scotched the little green men hypothesis.
August 6, 1967, a newly commissioned radio telescope picked up a distant radio signal. They weren't expecting any such signal, so scientists quickly dismissed it as an interference.
Switched on the high-speed recorder and it came blip, 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 blip. Clearly the same family, the same sort of stuff.
But something was different about this signal. The behavior suggested that there was something else at play. So scientists looked more closely and found that these signals appeared at a similar declination and right ascension. Further investigation revealed what we now know as pulsars, a special type of neutron star that rotates. But what are pulsars and what does their discovery mean for the present and future of our universe? Join us as we explore the science of pulsars, the cosmic lighthouses. After several decades of space exploration, we can finally say that we know enough about our universe. But the reality is, despite the level of unprecedented knowledge that scientists have gathered, they'll be the first to admit that we've barely scratched the surface. Most of what we know centers around us. It's a very tiny part of the whole universe, and it will take us thousands and maybe millions of years before we grasp the majority of the cosmos. That leaves us with numerous space objects waiting to be discovered. One such object with that kind of status some years ago is the pulsar. But what are they? To understand what pulsars are, we'll have to touch on the scientists of stars like our Sun and how they disintegrate to form neutron stars. You're still able to see the world around you at night because of the stars. They shine bright and produce light because of their high temperature. And this temperature is a product of the plasma infusion that's happening inside these balls we call stars. Stars produce a relatively stable intensity of light, but atmospheric disturbances can make them twinkle occasionally. However, in the 1960s, scientists discovered a different kind of twinkling or flickering. Disturbances in the atmosphere are irregular. That means the twinkling of stars cannot be predicted. They just happen whenever the conditions allow it. This newly discovered flickering was different. It occurred at a regular interval. This showed that they were not just twinkling stars or terrestrial interference. Scientists call them pulsars. They are a type of neutron star. Those huge balls of energy called stars function through nuclear fusion. The core positioned at the center dissipates energy towards the outside, which offsets the pressure formed on the outside. These two parts work together, counterbalancing each other to keep the star intact. But the energy is not infinite. When a star exhausts its energy after 1,000,000 years, the two opposing forces can no longer offset each other. So the gravity from the outside gets a free rein towards the core, which begins to shrink, collapsing on itself. The shrinking core causes a significant increase in temperature to billions of degrees. So the core starts spinning, causing a highly charged magnetic field. When this goes on for a long time, the particles inside the core are compressed together and they start to merge. Electrons and protons start to combine inside the nuclei, giving rise to neutrons that emit a substantial amount of neutrinos. At this point, the neutrons begin to collide with one another until the core no longer has space to continue shrinking. What follows is a violent blowing away of the outside layer of the star. The neutrinos help to disperse the particles and we end up with a supernova. A supernova is a luminous star explosion consisting of the core and surrounding particles that could still give rise to new stars. The core remains in place. It's not a tightly packed neutron forming a small ball of matter. That is a neutron star, and a pulsar is a magnetized rotating neutron star, emitting beams of electromagnetic radiation from its magnetic poles.
A pulsar is a rapidly spinning neutron star, which is the small, incredibly dense remnant of a much more massive star.
The concept of neutron stars was first put forward by Fritz Zwicky and Walter Baldi in 1934. They posit that a supernova, the breaking apart of a star, would lead to the formation of a dense star consisting of primarily neutrons. The high density of neutron stars means a teaspoon of it will weigh higher than the tallest mountain in the world. Pulsars have been used to confirm the existence of gravitational radiation. They have also helped scientists to test other simple physics theories. As of 2008, 1,790 pulsars had been discovered, with the closest ones to us located many light years from our Sun. Other pulsating materials have been discovered by astronomers. One of them is the X-ray pulsar. This emitted powerful regular flares of X-rays. They are also magnetized neutron stars that choose their own rotational energy.
That we're picking up are entirely new. Nothing like this has been seen in radio astronomy before.
Unlike radio pulsars, their spin rate does not remain the same. It builds up by tapping energy from a companion star, which turns into a white dwarf after its resources have been spent. Neutron stars also form in different ways. For stars that orbit in pairs, a neutron star can continue revolution around its partner star. Planets orbiting around a star can also maintain this movement around the core of a neutron star. However, pulsars have been grouped into 3 distinct classes based on the electromagnetic radiation power source. Rotation-powered pulsars are those that derive power from a star losing its rotational energy. Accretion-powered pulsars are when the pulsar gets power from the accreted matter's gravitational energy. Magnetars refer to when electromagnetic power comes from the decay of a strong magnetic field. X-ray pulsars are rotationally powered. So, we've explored what pulsars are and how they are formed. How did we come to know of their existence? One person, Jocelyn Bell Burnell, is often credited with the discovery of pulsars, but this was not a feat she achieved on her own, or even intentionally.
That bit of the sky due to go through the telescope beam at 2 o'clock, 3 o'clock in the morning, December the 21st, perishing cold.
Jocelyn and other scientists have worked together to develop a radio telescope. This newly commissioned telescope was built to study interplanetary scintillation. That is, they wanted to see how solar wind affected the flickering of radio signals. It was supposed to help with the identification of quasars. What was even more remarkable at the time was that Jocelyn was a young graduate, even though she participated actively in the physical setup of the telescope and its management. Her supervisor was Anthony Hewish, a British astronomer who later won a Nobel Prize in 1974 for his role in the discovery of pulsars. Jocelyn was going through the telescope beam when the high-speed recorder showed a precise continuous radio wave signal. Hewish dismissed the signal as interference, but a more careful observation showed an unusual precision. The possibility of 2 little green men sending signals to Earth at the same time was almost non-existent.
So little green men, opposite sides of the universe, both deciding to signal to a rather inconspicuous planet Earth at the same time using.
Astronomers have never examined a similar astronomical object before this one. Jocelyn discovered another pulsar in December 1967. They concluded that it had to be a new cosmic particle. Another telescope confirmed the emission, which was measured to have an interval of 1.337 seconds. It was named CP1919, and the scientists proceeded to share their findings with the world.
It has to be some new kind of star, not seen before. And that then cleared the way for us publishing, going public.
Pulsars appeared in print for the first time in 1968. That was how we came to know about pulsars. Now, you may have heard scientists liken pulsars to cosmic lighthouses. Why is this comparison apt, and what does it have to do with the behavior of pulsars? Pulsars emit beams of electromagnetic radiation. They do so in a rotating pattern and at a regular interval. Just like a lighthouse, a pulsar is essentially a spinning neutron star, with radio waves surging from its poles. Like we explained earlier, the shrinking core of a collapsed star generates a tremendous degree of temperatures. It causes the core to spin, creating a charged magnetic field, which continues for a long time. You'll recall how Jocelyn Bell described the detection. It gives periodic beeps on the machine. That's because it's not emitting waves to all directions at the same time. Again, just like a lighthouse, which shines light at a specific spot while casting shadows in the opposite direction. The beeps that come from the observatory equipment happens when the pulsar is pointed towards Earth. Finally, pulsars rotate at a consistent rate. Its pulses are regular. The rate can vary from one pulsar to another, but each one maintains a precise spin rate, from milliseconds to seconds or minutes per rotation. So, we've discovered pulsars, but what are their significance? Pulsars are useful to astronomers for testing precision and existence of other scientific phenomena. Since they are stable and precise, they can help to highlight disturbances in other cosmic particles. For instance, pulsar timing arrays, PTAs, are employed to detect low-frequency gravitational waves. The behavior of pulsars is also key for understanding matter. Pulsars are also useful for testing general relativity. Pulsars have also been key for measuring the position of the Sun, determining the location of a spacecraft, establishing precise clocks, and examining interstellar medium.
The excitement was because this was a totally unexpected, totally new kind of object, behaving in a way that astronomers had never expected.
The discovery of pulsars has not only changed how we understand the world, it has provided new ways to confirm some of the discoveries we've made in the past. As for the future, the possibilities may be limitless. A better understanding of these cosmic lighthouses could open doors to newer discoveries that further enhance our knowledge of the universe. In pulsars, we have a nature-provided means of testing past theories and formulating new ones. If you enjoyed the video, click the like button and check out our channel for more deep dives into other cosmic wonders.